everyone, and welcome to the second lecture on gas laws. In this podcast, we're going to be going over the ideal gas law, Dalton's law of partial pressures, and Graham's law of effusion. This is a continuation of the very first podcast that you got. You should have your guiding notes in front of you, and let's begin. So, take a closer look at this formula. This is the formula from the combined gas law. Now, I want you to think about what it would look like if we took one whole complete side of this particular formula and plugged in some familiar information. So I want you to picture what it would look like if I took one whole side and plugged in as much information as I could with this little snippet of information. So on one side, for pressure, we can enter 1 atmosphere. Now, I mentioned this when you guys were doing your virtual lab, that you should probably write this down. 1 atmosphere is also equal to 101.3 kilopascals, and that is also equal to 760 millimeters of mercury. Now, millimeters of mercury is also known as torr. Okay. So this pressure right here could be, we could plug in 1 atmosphere. For volume, let's go ahead and plug in 22.4. For temperature, okay, STP actually means something. So STP, standard temperature, is 0 degrees Celsius, and standard pressure is 1 atmosphere pressure, otherwise known as 1 atm. That's the pressure that you get above your head when you're at sea level. So for temperature, make sure you realize that whenever you're using the combined gas law, we can't use degrees Celsius. We're going to have to use Kelvin, so add 273.15 and plug that number in here. And for N, we're going to plug in 1 mole. So right now, if you don't have a calculator, you should probably pull out a calculator right now. I want you to actually plug those numbers in and tell me what the left side of this formula is. Go ahead and pause the vodcast if you need to at this time. So, how the ideal gas law constant, R, was made is very simple. If you take that one expression on the left side of the formula of the combined gas law, and you start plugging in all of these constant values, you can get a number that will always be the same every single time, as long as you're talking about STP. 1 mole of gas at STP is equal to 22.4 liters. So we can change one whole side of the combined gas law, since it's a constant value now, you can change that to be a symbol, and we symbolize that with a capital letter R. Now, I did mention this a little bit earlier, but in case you missed it, this is the conversions between all the different pressure units that you have. Now, why is that important? Well, if you think back to the entire left side of the combined gas law, you know, you plugged in 1 atmosphere, but you do understand that for pressure, you can have 3 different values of pressure. You can have atmospheres, kilopascals, or millimeters of mercury. So, you know what you're going to do is you're going to take the entire left side of the formula and just make sure you understand that this whole side right here, because P can have 3 different values, unfortunately, R then can have 3 different values. So in the previous problem, you stuck in 1 atmosphere for this value. But 1 atmosphere is also equal to 101.3 kilopascals. So if you plug that number in, the number changes slightly. So you should have gotten, for the one above, you should have gotten 0.0821 when you plugged in atmospheres. But if you plug in 101.3 for this value right here, you should get 8.31. Now, what if I change it again? And remember, these are all the same. They're all the same. 760 millimeters of mercury, they're all equivalent. If you plug in 760 millimeters of mercury, you should get this value on the bottom. So really, unfortunately, simply because we have 3 different values for, or 3 different units for pressure, you're also going to have 3 different values for R. So the ideal gas law, what I did is I took one whole side of the combined gas law and I simply replaced it with the capital letter R and rearranged the formula. What you get down here, PV is equal to nRT, this is the common way that when I ask students, I'm like, hey, what's the ideal gas law equation? This is usually what people will say. PV is equal to nRT. Now, the most important thing to remember is that when you use the ideal gas law, pay attention to the unit that you have for pressure. Because whatever unit you have for pressure right here, that is also going to determine which value of R you use. So let's see if you made the connection. If I have a pressure over on this side of the equation, if this is in atmospheres, if the unit here is in atmospheres, what will be the correct value of R that I should be using? Go back. If my unit for pressure is in atmospheres, the value for R that I should be using is 0.0821. Now what if I change my pressure and instead of using atmospheres, I choose to use millimeters of mercury. So on this unit of pressure, I've got millimeters of mercury. What number should I plug in for R? Well, if I have millimeters of mercury, I should be plugging in 62.3 from this value of R. So you see how the value of R is directly tied to the unit that you have for your pressure? Don't forget that. And also don't forget that T has to be in Kelvin, always. Volume has to be in liters, always. And N has to be in moles, always. The only two that really can switch around a little bit on you is the value of R and the unit of pressure. So here's a good example. You fill a steel container that has a volume of 20 liters with nitrogen gas to a final pressure of 2.00 times 10 to the fourth kilopascals at 28 degrees Celsius. How many moles of N2 does the cylinder contain? So let's grab a calculator and see if we can figure this out. Notice in this problem that you really only have one value for volume, you only have one value for your pressure, and you only have one value for your temperature. In other words, nothing's changing. So in order to solve for this, you're going to compare it to a standard, right? An ideal gas. 1 mole of gas at STP is equal to 22.4 liters. So we're going to be using the R, the ideal gas law. So the common way that we write the ideal gas law is PV is equal to nRT. Let's start plugging in some values. For pressure, they gave you kilopascals, and this is 2.00 times 10 to the fourth kPa. For volume, they gave you 20.0 liters. N, did they give you moles? Look, you're trying to solve for moles. So this is what we're trying to solve for. Now R, let's see if you really understood the material. Since your pressure is using kilopascals, what is the correct value for R that I should be plugging in? If you forgot, go back at your notes. Look, for kilopascals, you should be using the value 8.31 for this. This should be 8.31. And that was liters, kilopascals over Kelvin moles. That's the unit for the ideal gas law. And then for temperature, all right, don't forget, they gave you the temperature in degrees Celsius. So you need to make sure that you take 28 and you have to, do you remember the formula? You have to add 273.15 in order to convert that to Kelvin. All right, here's your formula. Now to solve, do a little bit of math, maybe some simplification if you need to, but I like to do it all on my calculator at the same time. You can always take the formula for the ideal gas law and try to simplify it to solve for whatever you're trying to look for. One of the words that we used on your virtual lab was the word derived. And derived means that you're going to take a formula or an equation and simplify it to solve for whatever you're looking for. And in this problem, we were looking for moles. So I wanted to be able to eliminate all the other things that were attached. So I wanted to solve for this guy. How do I get rid of this R and this T? Well, it's all attached through multiplication, so just do the opposite, divide. And really what I did is I have a derived formula sitting right here. So now what you're going to do is you're going to grab your calculator, you're going to start plugging in some values for your P and your V, And remember the correct value for your R and your T, and check your work with mine. So do keep in mind that sig figs are pretty darn important. And don't forget to convert your temperature to Kelvin. And when you do that, you should get 301 Kelvin. Alright, so notice how all of my units do cross-cancel. They technically all check out. The unit for R, that ideal gas law, was liters kilopascals over Kelvin mole. Alright, and when you go through and you realize that all of these units cancel, you will have only one unit left, and it's moles. And have you ever been told that a denominator of a denominator is actually a numerator? Oh boy, okay, so I know I'm getting kind of complicated here, but just basically trust me that all the units technically cancel, except for moles, and that's what you were trying to solve for anyway. Anyway, when you do this on your calculator, you're going to get a slightly different answer. Think about your sig figs and why I reported my answer as 1.60 times 10 to the second. The next gas law that we're going to discuss is Dalton's law of partial pressures. And you might be asking yourself, what's a partial pressure? Well, if you think about what all the particles look like that are a gas trapped inside of a container, well, now envision different gases, like a mixture of gases in the same container. Well, each gas is going to contribute a certain amount of power to the collisions that it has to the side of the container. Now, if we put more of one particular gas inside of that mixture, well then that particular gas is going to collide more often with the container, and so it's going to contribute more to the overall pressure. Well, one of the things to remember that's really important is that with this partial pressures law, it is dependent upon something called a mole ratio. So, for example, a tank of gas contains 3 different gases at a total pressure of 5 atmospheres. There are 2 moles of hydrogen, 3 moles of oxygen, and 6 moles of nitrogen gas. What's the partial pressure of nitrogen gas? So there's a strategy that you have to go about. Why don't we collect some more information from this problem? Let's kind of analyze it a little bit closer. Let's figure out the total number of moles of gas inside of the tank. You know that there's 2 of hydrogen, 3 and 6, and you add it all up, there are a grand total of 11 moles of gas inside the tank. We also know that the total pressure of the tank is 5 atmospheres. So what you can do is realize that the question is asking you for the partial pressure of nitrogen. Well, 6 out of the 11 moles that are trapped inside of that container, 6 out of 11 of it is nitrogen. That's a fairly large factor. In fact, it's the biggest factor out of all the gases that are in there. So what we're going to do is we're going to make a fraction of the whole. Okay, a fraction is always less than 1. So the mole fraction of nitrogen is technically 6 over 11. So 6/11ths of the total pressure is caused by the nitrogen gas. So on your calculator, just simply take 6 divided by 11, times it by 5, and you'll get your partial pressure for nitrogen. Here's a separate example. In this example, you have 2 grams of hydrogen, 4 grams of oxygen, and the total pressure of the tank is 1.5 atmospheres. So you need to revert back to what I just told you. Partial pressures depends upon mole ratios. I didn't give you any moles here. So let's think about some strategies. Step number 1. Since I gave you masses, why don't we convert those to moles? Step number 2. Since we have to make a mole fraction, you're going to need to figure out the total number of moles in the tank. Step number 3. Use a mole ratio and the total pressure to calculate the partial pressure of, think back, they wanted to know the partial pressure of hydrogen. Alright, so let's check your work here. You need to convert your 2.0 grams of hydrogen gas. Now what's the formula for hydrogen gas? That's right, it's H2. Alright, the molar mass is pretty easy. 2 grams is 1 mole of H2. This math is pretty easy. This is 1.0 moles of H2. Now, you also have 4.0 grams of oxygen gas. Now be careful. Oxygen gas is O2. Think about the molar mass here. You've got 2 oxygens, so double up the 16. 1 mole of oxygen here. Alright, so grab your calculator. This is going to give you 0.125 moles. But looking at your sig figs, it looks like I need to round this to 0.13 moles. Okay, of oxygen gas. Okay, so we just calculated the number of moles of each type of gas. That was our first strategy. The second step then is to figure out what the total number of moles of all the gases combined is, and then compare that to the total pressure of the system. So I'm simply going to add these two, and you can do that in your head. It looks like the total number of moles, total moles in the system, is 1.13 moles. All right, and they told us the total pressure of the system is 1.5 atmospheres. So in order to solve for the partial pressure of just hydrogen gas, I need to make sure that I do a mole fraction using hydrogen with the total. Okay, remember, this fraction should always be less than 1. In order for it to be less than 1, you're going to put the part over the whole. So this should be, in order to solve for the partial pressure, the fraction would be 1.0 moles of hydrogen over the total, which is 1.13 moles total. So here's your mole fraction. And then you need to multiply that by the total pressure, which is 1.5 atmospheres. Do this on your calculator and you will solve for the partial pressure of hydrogen. The next thing we're going to cover is the difference between diffusion and effusion. I know these words sound the same, and I think maybe you might have some familiarity with diffusion. Diffusion is easy. Like if I spray a bunch of perfume in the front of the room, you understand that those perfume particles would slowly migrate through the air from an area of high concentration, right, over by me, to the area of low concentration over by you. Right? That's called diffusion, and the smell would eventually reach you, but it would take some time for it to go through the air. The other word here, effusion, is much different. Effusion is the rate at which a gas can escape through a hole, like a tiny hole, like how fast it can leak out. And you're probably asking yourself, how does this apply to chemistry? Well, you got to remember, we talk a lot about gases in chemistry, and early on, a lot of these scientists, they like to study gases a lot. They found them very fascinating, very interesting. And you can't see them, which makes them even more interesting. All right, another thing to remember is that effusion is really important for certain parts of your life. Like right now, if I took you guys all scuba diving, you would want to make sure that the tank that they gave you was mixed properly with the proper pressure and the proper amounts of each gas to so that you could dive for a specific amount of time. And right now you technically are breathing a gas right now that has been circulated through an air vac system and delivered to you in this room. So yes, this does pertain to your everyday lives. So Graham's law. There is a law that goes along with this concept of effusion. It states that the rate of effusion is inversely proportional to the square root of the gas's molar mass. Say what? Alright, we'll talk about what that means in a minute. But here's something critical. Gases of a lower molar mass will effuse faster than gases of a higher molar mass. So the little guys are able to sneak out of the container faster than the big ones. And there's a key component to this particular gas law, a stipulation, if you will. These gases, if they're in the same container, they have to be at the same temperature for this gas law to work. Right? So temperature has to be the same. And then I have a little picture down here. If you look on the left side, it looks like you have a mixture of two different gases. And here is an opening from here to here. And you'll notice that it's the little one that seems to be leaking out faster. Try to remember that. That's a crucial part of this gas law, is that the little guy, the guy with the smaller molar mass, will be able to leak out of the container faster. Here is Graham's law. This is the actual expression. So when I told you that it's the inverse of the square root of the molar masses, ooh, okay. So the rate of particle A is on the numerator, but its mass is on the denominator, and you of course see the square root. So here's particle B on the denominator, and we flip it over to be on the numerator. This is the physical expression of Graham's law. Well, how do we use it then? Well, let's give you an example. Compare helium to nitrogen. First of all, helium's a noble gas, and so since he's a noble gas, his molar mass only includes one helium. All right, so his molar mass is only 4 grams per mole. Now nitrogen is technically N2. All right, so you're going to have to double the mass of nitrogen, which is 14. So double that, and that makes 28. Right off the bat, without doing any math, I can tell you that helium will leak out of the container faster. Do you remember why? Because helium has the lower molar mass. So right off the bat, I know helium is going to leak out faster. And if I ask you, how much faster? Now we get to math, okay? For Graham's law, you typically put for the rate, you typically put the small guy on the numerator and the big guy on the denominator. But the most important thing to remember is that you know that the little guy is faster, right? So when you get your answer at the end, this number right here is just basically a ratio. Okay, it's like a number. So if you have the fast guy on the top, this number over here better be greater than 1. Okay, so that's how you can check your work. Always put the large number on the numerator and the small number on the denominator. So in this particular question, if you go ahead and you can check this work if you like. I encourage you to do that to make sure that you can find your square root button. This basically says that helium is going to effuse faster. How much faster? Well, about 3 times faster. Technically 2.7 times faster than nitrogen. So if I've got a mixture of helium and nitrogen at the same temperature, I'm pretty much guaranteed that the helium will leak out 3 times as fast as the nitrogen.